On the first video, we worked on a PNG parser from scratch that takes any file and gets its structure. And on the second video, we analyzed its performance with the line profiler, and we got a few insights on what was going on and how we could do things a little bit better so that it would run a few times faster, 2.7, almost 3 times faster. And I actually left the console open from that time, and I have all the code that we had before. So we had a few imports, and we had a regex, and we had the valid ctype function, and then we had two big things, actually not in that order. That's the order that's in code. Yeah, well, I should really run that thing in order. So what we worked was not copying things around that we didn't need. And usually when we work on code performance, on code optimization, not doing things is the best way to get good performance, especially not doing things that we don't need. So this was the last thing that I checked. If we were running with this copy not as intensive as it originally was, and we were not getting the CRC32 calculated, because maybe we can assume that the files we're processing are all well formed, and that's something that on normal situations, on normal circumstances, we can effectively assume. Then we can gain a little bit of a speed up. We were getting 60% faster run times with this, or actually 60% faster validation parsing speed from this. And the idea was that if we were able to actually not copy things around, we would get an even more substantial speed up, right? Because if we take a look at the output from line profiler here, sorry, we can see that 45% of the time is being spent copying things here, right? When we define what the data that we're going to parse actually is. And then 40% of the time, almost 40% of the time, is being spent here saying, okay, actually this is my data, right? For this chunk, this is my data. So about 85% of the time is being spent copying things around. And I said that if we had a way to get the bytes that we read from the file and have our function work on it without copying them, that would be the ideal case for this. And if you try to think about that, it may seem like we have to do something really complicated, because how are we going to do this, right? We could maybe, I don't know, try to decode these few bytes without copying them. Is there a way to do that? And what about here? This was the copy, this is the decoding. Is there some way to get str, the str function, right? To convert these things into string without having to call decode? Or maybe, well, maybe no, we cannot call decode on just a big buffer and give it an offset, because that's not how it works. All right. So it looks like we are stuck on a place where we cannot really do things, or we cannot get to that point where we want to go. And there's actually a very simple way to do that. And it may not seem intuitive because until you've worked with it, you probably didn't heard about it. But Python has what's called memory views, right? And if we do things right, if I write memory view right, instead of passing the data just as it is, I can pass the memory view over the data. And you can see that the function ran exactly the same, the results are the same, and everything looks like really happy, really great. But there's actually a bit of a trap here, because if I wrote, let's say, if I wanted, let's use some accents, like that. If I wanted to encode this as UTF-8, right, it's going to give me this this sequence, right? And if I had that, I could do, hey, you know what, decode that as UTF-8, and that works. But if I had the memory view over those bytes, Python's going to tell me, you know what, you cannot do this. Memory views do have a 2 bytes function though, and you can use that to get bytes once again. And another thing that we could use is the bytes function, the bytes constructor, and we're going to get the same result. Now, this looks like I'm rambling around memory views and things, but you can actually see that one of the changes that I had done before was exactly that, converting things to bytes. Specifically, things where I'm going to call the decode method over. So this was a little change that I had done in the code for the previous video that I didn't explain, and it has to do with this. Because of this line right here, we can effectively receive either a bytes object or we can receive a memory view. And all the rest of the function is working effectively the same. Now, there's a little bit of a trap here. I'm going to call it chunks 2 because I still have the previous one. And if I were to get the first chunk, the second chunk actually, not the first, and we can see that this one has all the information that we want for the text, the comment chunk. But when we use the memory view and we try to go and see the data, we're finding out that there are no bytes there. There's just a memory view, and we have to get this converted into bytes for us. Why is that? Memory views work with the buffer protocol in Python to effectively pass a view, a reference. You could think of it as a pointer, but it's not really a pointer because you cannot do the weird and safe things that you could do with pointers. right? So it's not a pointer, but you get a reference to the underlying buffer of the object, right? The memory view exposes the underlying buffer of the object in such a way that you can pass the memory view around without having to copy things. And when you want to access the data after that, you don't have access to the bytes themselves. You have the memory view. So if you want to work on bytes, you have to convert that back to bytes, okay? But it looks really complicated. So what did we gain with this? Let's compare things, right? If I were to time the parsing of this PNG in particular, if you don't remember, it's about 1.30 something megabytes, 1.36 megabytes, give or take. So we're doing it now over 1.63 milliseconds. This is really fast. And that's at about 832 megabytes per second. What if we were to do it over the memory view? And I think it's not going to be a spoiler if I say it right now. It runs faster. It runs about what we had before, 1.63 milliseconds, and now it's running at 670 microseconds. So it's 2.4 times faster. And back from before, we're 2.7 times faster. We're about 6.5 times faster than our original code. Because first we took the time to not copy things or minimize how many copies we made of things. That's what we did on the previous video. And now, using memory views, we're effectively not doing any copies. Actually, that's a little bit of a lie. When we call bytes over here, that's the only one copy we're doing now. And so before we were copying many times round the contents of our file that we had read completely into memory. And now we're just copying 4 bytes for every single chunk. So we have 25 chunks, we're copying 100 bytes. The rest of the code works effectively the same. And if we were to see with the lprun what goes on when we work over the memory view, like this, and let's do it over raw data so that we can compare both things. So if we work over raw data, the bytes objects, we have 77% of the time, and 25% of the time, about 32% of the time is being spent on copies. And this is also another copy that's shadowed in there, that's hidden in plain sight. And we can see that calculating the CRC before took 57% of the time, and per hit 557 microseconds. Remember, our unit is 1/10 of a microsecond, so 570 is actually 570 tenths of a microsecond is 57 microseconds. And now we're down to 25. Why? Well, because this was a copy, and a copy that we're now avoiding. Not only that, we can see that the CRC32 now takes 75% of our time. So if we were to run again with memory view, not that, if we were to run with time it, and running over the memory view, 672 microseconds, and we turned off the CRC calculation, we could expect to go about 4 times faster at least, because 75% of the time was being spent there. And it's actually sorry about that, 9.5, 9.6 times faster even. Okay. So that's really something. I did not have the time to really dig, or actually I did try to dig deep into this, and it's a deeper rabbit hole than I expected. Setlib, Python's setlib module wraps around the platform's setlib library, right? So there's setlib for Windows, setlib for Linux, setlib for Mac OS, and setlib is really a great piece of code. I cannot understate that. So it's very well written, and it works wonders. So I do have the feeling, and this is something that I should research and investigate a little bit further, I do have the feeling that probably Python, when it passes data to setlib, it could be passing a copy. I don't have the evidence to support that yet, but I believe that's something that could be happening, perhaps in the name of thread safety. And that's something that's really, really important to consider here. Python in general is written in such a way that everything is safe. There's the GIL, the global interpreter lock, the infamous GIL. And actually all that thread safety, all those things from Python are fantastic for programmers, because we don't have to worry about race conditions, we don't have to worry about locks, we don't have to worry about anything. We just write our code and it runs. So I did a few experiments trying to implement CRC32 calculations. None of those got me any good result. Well, the results were valid. I was able to get the same CRC32, but they were slower, much slower than setlib. And there's still one thing that I didn't try, which is the having it written in Python and taking good care. And there's something that I've been trying to pull off, and there's something that I've been trying that I didn't get it to run and there's something that I've been trying that I didn't quite get it just yet, that is writing a Python CRC32 table lookup calculation. That's actually how all the fast CRC32 calculations are done. You can run it on a bit level, and that's the conceptually easy version. But the problem is that you are effectively doing bit fiddling inside a for loop, and even if you do it on C, it's really slow. And because all the operations that are involved in CRC32 calculation are actually exclusive ORs, right? So XORs. You can work out what a succession of XORs, you can actually work out what a succession of XORs ends up being, because, you know, XOR something and something and something and something, you can figure out what everything is, because if you have many things XORed in between each other, you can actually get, oh, so at the end of the day it's XOR against this thing. And yeah, like I said, CRC32 does XORs and bit shifts, and that's all. So the table approach lets you figure that out. And then there's the crazy stuff, because of course there's going to be crazy stuff. There are a few really fast implementations of CRC32 that play with the idea of using CMD instructions and also threading. And so you can thread depending on your CPU's microarchitecture and how many cycles a specific instruction takes. There are people who are so beyond that figure it out. Oh, so with 3 threads, we can run 3 threads in parallel, and we chunk our data this way and this way and this way, and we can run effectively 3-4 times faster. And that's really much further beyond than what I can effectively do with Python. But at the end of the day, this is what I wanted to leave you with. If I were to use the simple code, the original simple code, I can get to 5.13 milliseconds. And let's be fair, let's work with CRC32 here. Using memory views and minimizing our data copies, we can get down almost to 670 microseconds. But does it really make sense? Do we have to do all that work trying to minimize things? Or maybe, just maybe, if we used memoryview from the start, we could have gotten about the same result. And I think that's something really, really interesting of using memory views, that I don't have to change the code to reap the benefits, right? The only thing that I had to do was declaring or instantiating C-type into bytes right as we start the parsing. And I think this is also something extremely important. I got a 7.5 speed up in the code just because I noticed that there were so many copies being done in memory, and found a way in which I could minimize that. And this is important only because we're reading files and we're trying to parse things and figure out something about the file that we're analyzing. So if I were trying to decode the file and get an image out of this, it wouldn't really make sense to do this, because I would have to convert all the information into bytes, right? I would have to do something with those bytes. I would have to read them to get the numbers that represent the colors. I would have to follow all the PNG decoding sequence algorithm, right? So I can get away with this just because I'm interested in the structure of the file. And if we were to convert this into some sort of speed, that would be the number, right? Is that right? Yeah, that's right. Yes, 2 gigabytes per second. But I was just thinking, because if we turned off the CRC32, we can go to really huge numbers, like 20 gigabytes a second. So same as before, but this is actually 705, like that, 19 gigabytes per second. And it can seem like it looks really crazy. Why do I care about this, right? Why does it matter if we're reading at 2 gigabytes, if we're processing at 2 gigabytes a second or 20 gigabytes a second? And that's important up to a certain point, because really in all this, the bottleneck is always going to be the speed of the drive where we're reading from, right? So if I'm reading from a serial data 3 drive, that can give me 500 megabytes a second. The normal code that minimized copying, the original code was not up to that task, right? Because it was a 200 and something megabytes a second. It was going to be our bottleneck, right? And the version we did later that ran almost 3 times faster, that was enough. Okay, that could work at the speed of serial data. But if we're on an NVMe drive, then 700 megabytes a second is not really going to be good, because the drive is going to go faster than us. So that's why we can resort to the memory view trick. Let's call it a trick. And that's going to give us a bit more than what we need, right? And it's going to help our code keep up with that. Because, again, the code is doing not exactly the same. My bad there. Because if we were to access the data for a chunk, we would have to convert it to bytes, or we had to access it in some way that to make it readable. But the end result that we're getting is the same. And then there's the CRC32 calculation. That's really something that's still a little bit beyond me to get it really working on. Like I said, I have a few experiments in Python that maybe can help us get there. But that's about it. But even then, if we know that we're working with valid PNG files and we don't want to check the CRC32, we could go a step beyond and say, okay, we're not going to check the CRC32. And if we were on that situation, let me see with lprun and flag, let's set it to false. If we were in that situation, what would be our next move, right? We don't really have many things to do. Okay, so we could work a little bit on the decoding of the C-type. Maybe we could even try not even to validate it, but we're really reaching the limits of what can be effectively be called parsing a PNG file at this point. So there's some work that we're going to have to do. Okay. And another step that we could take at this point, yes, we could try to do things with Python at this level, right? Because we're probably going to bump into the interpreter, right? Like I said, this is tenths of microsecond, so about every single line of this takes half a microsecond, a third of a microsecond, or almost 1 microsecond, 2 microseconds here, half, a little bit more than half, a third. And even though that sounds really fast, that's about the limit of what we can reach with Python, at least on this computer, right? Every single instruction that we do is going to take something around that time. And if we need to go faster, then we would definitely have to go to a compiled language. But I think this was a very interesting experiment to try and do things around. And at least break some expectations that with just a little bit of change and effective use of memory views. I love that the docstring doesn't really say anything about it. It just says, hey, okay, you're going to get a memory view out of this. Sorry, I got off road a little bit there. So by taking notice that what was actually expensive about our code was actually the copies in memory, we could effectively make it run 7 times faster. And if we were to be fair, let's be fair, and run this, remember this is the original code. I'm just passing the memory view. That's 70 microseconds. That's really fast. Without checking CRC32 against the original code that did a lot of copies around, well, we get about 70x faster just using memory views, right? Why? Because most of the time there was being spent copying things that we didn't really need.